This lesson, we're going to look at solving logarithmic equations and natural logarithms as well. And so just to want to remind you that a natural logarithm, or excuse me, natural exponential, has a base of e. E is our natural base. So when we're solving this natural base e exponential function, we're going to use what's called a natural logarithm. So first, let's just take a look at this chart. Here's an example of exponential form, and here we're converting it to our logarithmic form where the log, the base b, we have our solution, and here is our exponent. So the base, the solution, the exponent. We learned in another lesson that this is what we call a common logarithm when you have a base of 10. Now, we don't generally write it with a base of 10, we just leave it blank, but it's implied that that is a base of 10. What we have for natural logarithms is if we have base e of our exponential, we have base e in our logarithm, but we don't write log base e. What we write is the letters ln. So instead of seeing log base e, we just write ln of x. So how can we simplify our natural logarithmic expressions? The same rules apply with our properties of logarithms with natural logarithms. So if you just remember, we have our product property, where if they're multiplying here, you can add the logarithms, common base. If you see division, that's our subtraction of logarithms. And our power property, if you have a log of base b of some number raised to a power, that power comes to the outside and is multiplication. So we can simplify these the same way. I see here it says 2 times the natural log of 15 minus the natural log of 75. So I can use our power rule first to move this 2 times the natural log of 15. So it'll become the natural log of 15 squared minus the natural log of 75. Now that we see subtraction, I can now use our quotient property. So let me write this. This was power property first. And then I'm going to use the quotient property. So I'm going to write this as the natural log of 15 squared over 75. So real quickly on our calculators, 15 times 15 is 225. The natural log of 225 over 75. And you can simplify that by dividing it. You would get the natural log of 3. And you can leave it as that if you're leaving it as one single logarithm. Let's take a look at a few examples. Write each expression as a single logarithm. I can take this one here and use our power property to write it as the natural log of 7 plus the natural log of 5 squared. I'm going to simplify that real quick. And then for our next step, this is what we call the product property. So since they're adding the natural logs, I'm going to multiply in the same log. So this is going to be 7 times 25. So we're going to get the natural log of 175, and you can leave it like that. For this one, we have our, again, power property. We can also see that this one already has the product property, but we're trying to put it into single logarithm, not expand it. So I'm just going to use the power property, and then I can see here there's going to be a quotient, and this one's a power as well. So first I'm going to move those, the 3 and the 2 for the power property. So this will be ln of x cubed minus the natural log ln of 2x squared, making sure that this whole 2x is in parentheses. So then for our next part, I'm going to write ln, or natural log of x cubed, minus the natural log of 4x squared, because it was 2 squared and x squared. Now I'm going to use my quotient property, the natural log of x cubed over 4x squared. And this can be simplified a little further. We have x cubed divided by x squared. So what you're going to be left with is, I do keep doing that, ln of x over 4, right? Because there's 3 of them here, x times x times x. There's 2 on the bottom, so this will get eliminated, and you're only left with 1. So 1x there, or 1/4 x. For this one, I see product properties, I see a power property. I'm going to use the power property first. ln of x cubed plus the natural log of y squared plus natural log of 5. Now I can use our product property to write natural log of x cubed y squared times 5. And just to clean that up, I'm going to rewrite it 5x cubed y squared. The next section in this lesson is solving exponential and logarithmic equations, including eventually our natural logarithms, but we'll get to that in further videos. First, we're going to start with how do you solve exponential equations, and we briefly touched about this in our previous videos. One of the methods is finding a common base. So you can see here, if we're going to solve this exponential equation, 16 raised to the 3x equals 8, I can actually find a common base between 16 and 8. I can change 16 to equal 2 to the 4th power, and I can change 8 to equal 2 cubed. Right? So the common base in this example would be 2. They have that nice common base. So because of that, using our exponential properties, I can say 4 times 3x is 12x, and this is going to be our 3. They have the common base, you can see here as 2. Therefore, I want to create an equation where 12x equals 3. So 12x equals 3. I can divide by 12 on both sides, so x would equal 1/4, or 0.25. I can always take this number, this solution, and substitute it back into the original problem, and it will equal our solution here. So just real quickly, we'll check. 16 raised to the 3 times 0.25, and I get my same solution of 8 back again. What is the solution of 27 raised to the 3x power? And it's going to equal 81. So here we have 27, 3x power equal 81. I want to find a common base of 27 and 81. That common base would be 3. 3 cubed is equal to 27. And that's going to equal 3 to the 4th power. So when I can simplify this, 3 to the 9x equals 3 to the 4th. Here are my exponents. They have the common base. So now 9x equals 4. We're going to divide by 9 on both sides, so x equals 4/9. Be careful changing this to a decimal. I understand that this is 0.44 repeating, but when you check your solution, if you just write 0.44 and round it, you're actually going to be decreasing the value. So it's going to be less than 81. So to check my solution, what I'm going to do is I'm going to write into the calculator 27 raised to the 3 times, another parenthesis, 4 divided by 9, close parenthesis, equals, you will see it equals 81. So I just wanted to write the fraction into the calculator rather than changing this to 0.44 because that will be less than 81 when you check it. So just be careful there. Let's solve an exponential without a common base. This is where you will have to use your calculator. You will have to use the logarithm key on your calculator. I'm using a TI-34. You may have to do separate steps using your iPhone, but we'll take a look. So right here, we don't have a common base between 15 and 285. 15 squared, 15 cubed, right? We can't get to 285. And this is not a perfect square either. So we're going to have to use logarithms to solve this exponential. Your first step when given this exponential is to take the log of both sides. Now you could take the log base 15, of both sides, but eventually you're going to have to do the change of base formula. So one thing you can do is just take the log base 10 of both sides, the common logarithm. So this is really a base 10. What I'm going to do here is use the power property to move this exponent to the outside of our logarithm. So log base 15 of 3x becomes 3x times log of 15. And then the log of 285. You have to take the logarithm of both sides of your equal sign. So at this point, since our goal is to isolate the variable, I'm going to divide by 3 log 15. And you can do the same thing on the other side. Now, at this point, you could plug this right into the calculator, or we could actually take an additional step. I'm just going to write 3 log 15 for now. What you could do is, using the power property, move this 3 back into this exponent here to be 15 times 15 times 15, and then divide your logarithms. But the nice thing is that if you have the TI-34 or something like it, and you can use parentheses, you can come out to the same solution. So I'm going to do the log of 285, close parenthesis, because you don't want to take everything within one logarithm, so make sure you're closing that parenthesis. And I'm going to divide it by, I'm going to create another grouping here, open parenthesis 3, log of 15, close parenthesis, so now that's the log of 15, close parenthesis again to say everything is being divided, and hit equals. My answer is going to be 0.695763712. So I'm going to round this, let's say, to the nearest thousandth. So 0.696. X is about 0.696. I want to just check my answer. 15 raised to the 3 times 0.096. Oops. 0.696. And I get 285.5. That's pretty close. Now it's a little much because I did round up on this solution, so it is going to be a little higher, but that is very, very close to what the solution was. If I had chosen to round it out a little further, it'd be a little more accurate, but this is pretty good to the nearest thousandth place value. Let's take a look at an example. What is the solution of 5 to the 2x power equals 130? So we got to solve for the missing variable here. So I'm going to write 5 to the 2x equals 130. I'm going to take the log of both sides. So the log of 5 to the 2x equals the log of 130. Using our power property, I'm going to move that exponent outside here. So 2x log of 5 equals the log of 130. I want to get the variable by itself, so I'm now going to divide by 2 as well as divide by the log of 5 and do the same thing on the other side. So what you're left with is x equals log of 130 over 2 log 5. Now again, here you could write this as the log of 25 because this would be 5 squared, but I'm just going to leave it like this so I can plug this into the calculator. So the log of 130, close parenthesis, divided by, open parenthesis 2, open parenthesis, log 5, close parenthesis equals x is about 1.512. So let's check our solution. 5 raised to the 2 times 1.512. That's very, very close. And remember, I rounded, so this is just going to be just off. So this is a pretty good solution.